Hello everyone. So in this pre-lecture tutorial we're going to be discussing what we call the solubility product constant. Essentially the solubility product constant is yet another form of the equilibrium constant, where what you are actually describing is the dissolving of what would be a sparingly soluble or what's considered to be an insoluble salt. So essentially what we're going to do is talk about strategies how we can calculate Ksp values and also how to use those Ksp values to calculate the solubility. Because it's important to differentiate. The solubility product constant, again, is another version of the equilibrium constant, but it is not the solubility of a salt itself. The solubility of a salt actually refers to the quantity of that salt that dissolves in a saturated solution. And so let's begin by actually working to calculate a solubility product constant for an insoluble salt. So in this example that's on the slide, I have gold 3 chloride, and I'm told that the molar solubility in a saturated solution of this salt is 3.3 times 10 to the negative 7th. Usually, these molar solubilities would obviously be given in units of molarity. So I'll go ahead and amend the text of the problem to reflect that again this 3.3 times 10 to the negative 7th is supposed to be in units of molarity. So let's actually start off by writing the equation that shows the dissociation of this sparingly soluble salt. So I would have gold 3 chloride as a solid, and the dissociation then would be an equilibrium process that would give us gold 3 plus cations in aqueous solution, as well as 3 moles of chloride ions also in aqueous solution. And so, since this is an equilibrium process, we can't, as usual, do our bookkeeping in terms of amounts involved in this equilibrium process utilizing an ice table. And if you recall, for heterogeneous equilibria, solids are actually not included in the equilibrium constant expression, and so it wouldn't be necessary to actually track the amount of solid that is present within the equilibrium process because of that. And so if I think about my initial conditions, when I first put the gold 3 chloride in solution, there wouldn't be any gold 3 plus cation or any chloride ion. But obviously there would be some change, and ultimately that change results in a molar solubility of 3.3 times 10 to the negative 7th molar. And so this solubility would actually be what would correspond to our X value, or our change, within the ice table. But we have to be careful because the stoichiometry here is not 1 to 1. It's actually 1 to 3 in favor of the chloride ion. And so the molar solubility actually refers to how much of the gold 3 chloride dissolves. So it would be equivalent to X exactly. In other words, where I would have a coefficient of 1 within my equilibrium equation. So basically that would mean that this value of 3.3 times 10 to the negative 7th would go here. It would be the equilibrium concentration of the gold 3 plus cation, because again that reflects a single mole of change, if you will, within the equilibrium process. Okay? And so that's where the molar solubility would go. Wherever X would go in the table, that's where the molar solubility would be inserted. And so that means that when I actually calculate the change for the chloride ion, since there's a coefficient of 3 in front of the chloride ion, then that change would be multiplied by 3. Okay, if I multiply 3.3 times 10 to the negative 7 times 3, I get 9.9 times 10 to the negative 7th molar is the concentration of the chloride ion. So to calculate the Ksp, again, it's an equilibrium constant of a sort, and so you're still going to use the law of mass action. Basically, it would be your concentration of gold 3 plus ions in solution times your concentration of your chloride ions in solution cubed. And then it's just a matter of inserting each of these concentrations into the proper place within our Ksp expression. So that would be 3.3 times 10 to the negative 7th I'm going to multiply that by 9.9 times 10 to the negative 7th, but then cube that. And then once I actually do this math, basically my Ksp value ends up being 3.2 times 10 to the negative 25th. Now that's an awfully small number, but again, remember that basically there's very little of the salt that's dissolved. Basically, 3.3 times 10 to the negative 7th, that's less than 1/1,000,000th of 1 mole per liter. And so it would make sense that this Ksp value would be very small, considering the very small amount of the salt that actually ends up getting dissolved. Now, what about if I actually want to calculate a molar solubility given the Ksp? Well, that's another ice table type process. So I'll go ahead and demonstrate it. Suppose that I wanted to calculate the molar solubility of a saturated solution of lead-2 iodide. Well, in that case, what I would need to do is, once again, it's always helpful to have a balanced chemical equation reflecting our process. And so again, since this is such a tiny value, then that means that, again, this is probably going to be an equilibrium process. And also, since we're working with a saturated solution, that also makes this an equilibrium process that will give lead-2 plus cation, so the lead iodide would be in solid form, the lead-2 plus cation would be in aqueous solution, and then I also get 2 moles of the iodide ion, also in aqueous solution. And so I'm going to start to construct my ice table. Again, I'm going to line out the spots that would correspond to my tracking the lead iodide amounts, since again it's a solid and wouldn't appear in my expression for Ksp. And initially, again at the very beginning when I put the lead iodide in solution, I wouldn't have any lead cation or any iodide anion at all. But we do know that some of this salt will dissolve, and so the change is going to be plus X for the lead-2 plus cation and plus 2X for the iodide anion. And so that makes my equilibrium concentration expressions for each ion X for lead-2 plus and 2X for the iodide anion. And so to solve for the molar solubility, we're really looking to solve for this X. And so I'll go ahead and construct my expression for Ksp from the law of mass action. So that would be my lead-2 plus cation and my iodide ion squared. And so if I substitute that in, that's just X times 2X the quantity squared. That's 4X cubed. And so that 4X cubed will be set equal to our known value of Ksp. So 4X cubed is going to equal 1.4 times 10 to the negative 8th. And then I'm going to divide both sides of this equation by 4. So that means that X cubed is 3.5 times 10 to the negative 9th. And then I'm just going to take the cube root of both sides in order to solve for X. And when I do that, I get an X value, or a molar solubility, of 1.5 times 10 to the negative 3rd molar. And so go ahead and work on the follow-up assignment that corresponds to this pre-lecture tutorial. If there are any questions, again, please feel free to email. We'll obviously be discussing this in class. Again, if there are any concerns, also feel free to reach out to me as well. All right, have a good night.